Hey guys, today we are doing a video on A-level physics, nuclear physics A2 topic. And in this video, I will read the syllabus requirements as well, just to make sure that we don't miss something out. So that both of us get a clear idea of what exactly do we need. And if there's time left, we will also do some questions about nuclear physics. They're fairly simple once you get the hang of them. Right. So 26.3 mass defect and nuclear binding energy. Now for many of you, these two terms won't mean anything, and that's alright, because that's the purpose of this video. Nonetheless, I will give you a brief idea of them before going at them in detail in the rest of the video. So the mass defect is formally defined as a difference in mass between the mass of a particular nuclide and the mass of all of its separate individual nucleons. Interesting, isn't it? For those of you who are familiar with the term nucleons, you'd know that nucleons are basically neutrons and protons, all of the neutrons and the protons that make up a particular nucleus. And the nucleus is basically just all of those neutrons and protons. So many of you may be thinking that if the nucleus is basically just all of those individual separate entities, all of those individual separate protons and nucleons together, then why on earth is there a difference between the compound nucleus and the sum of its individual components? You're right to be confused, and that is basically the purpose of this topic, to explain something to you that might be a bit hard to accept but will make sense. Another thing I want to tell you at the beginning is that there's a concept that energy has mass. Again, you're likely befuddled. I was too, as was a lot of other people. So I will elaborate on that one as well. Now, what is nuclear binding energy? Well, it is formally defined as the amount of energy needed to separate out all of the nucleons, or basically the amount of energy needed to dismantle a particular nucleus. That is, we don't want the nucleus to be whole anymore. We want to separate out all of the nucleons that make up the nucleus, so that they aren't one complete whole anymore. Rather, they are separate components, independent of each other, that are not exerting any type of influence on each other. That makes sense. And at the beginning of this, it would be easy if you were to realize, if you were already aware or became aware when I told you that there is something called a strong nuclear force which is present within the nucleus. And what it does, it's basically the force that keeps the nucleus together more easily. It keeps the protons together, even though they're all positively charged, and yet they form one compound entity. Even though one might expect that they would be repelling each other and attempting to be as far away from each other as protonally possible. I don't know. Yeah, bad joke. So but they aren't. They are just there, and that has to do with the strong nuclear force. And basically, this nuclear force is what makes the nucleus stable, because we all know that there are some unstable nuclei, and those are the ones that are decaying over a period of time which is actually typical of the nucleus type. For example, we have the C12-6 and we have C14-6, the second one being an isotope of carbon which, unlike the normal one, is radioactive and decaying over a long period of time. I don't really remember how long, but just a long period of time. So from this you might get the idea that the stronger the nuclear binding energy, or the higher the value of the nuclear binding energy, the more stable the nucleus would be, because the more stable, because the more powerful the nuclear force would be, and hence the more compact the nucleus would be, and hence less likely of that particular nucleus to disintegrate via whatever type of radioactive decay process, right? But as you all know, all of the different nucleuses, they have different nucleon number, so it would be obvious that the number of nucleons are also having an impact on the nuclear binding energy, and not just the nature of the nucleus. So comparison might be a bit difficult, right? Because we may compare a carbon and an oxygen, and we may say that nuclear binding energy, say if carbon is higher, I'm not really sure, and we say that it's not, how are we to say that carbon has a stronger nuclear force? I mean, the number of neutrons are different, and they may also have been impacting the value of the strong nuclear force, and you can't be certain that it is because of the type of the nucleus. So that is why we calculate something called nuclear binding energy per nucleon, so that we're capable of comparing the nucleon binding energy of various nucleuses. So hopefully you're onto a solid start. So hopefully well defined, and number one, we have to show an appreciation of the association between energy and mass as represented by E is equal to mc square, and recall and use this relationship. So previously we were told that energy is always conserved and so is mass, and yet sometimes this theory came into question, most prominently when we realized that there was a difference in the mass of the dismantled nucleus and the mass of the complete unaltered nucleus, and the mass somehow disappeared, or apparently disappeared, without any byproduct being projected off, and at this point the mass conservation principle came into question, and all of those principles that we so blindly believed in for thousands of years and based everything on didn't seem all that solid anymore. And the question arises, is perhaps the mass conservation principle not as true as we believed? No, it definitely is. But if it is, then how do you explain the difference in the mass? Well, one way of explaining this would be to say that energy has mass. And that is good if we find it a bit difficult to remember. But a better way to remember this is to say that energy and mass are both conserved, in the meaning that the total energy and mass is conserved, meaning that the two quantities are actually interconvertible and the total is what is conserved and not necessarily the individual components, that is energy and mass, conserved by itself. The total of them is what is conserved. And this explained helped us understand the concept of the mass defect. So, when we do work on something, for example, we may lift up a bucket, the potential energy of said bucket would increase, right? And so, if you had a sensitive enough balance and you took the measurement of the bucket at a higher altitude and the one at the lower altitude, you would observe that there was, though a minor and yet significant increase, and that would literally be in the 1/1,000,000th of the actual mass and would require great precision, but there would in fact be a difference. But how on earth did the mass of the bucket increase? There wasn't anything else being added onto the bucket. It just seemed to increase out of nowhere. And one becomes confused. But if one were to question as to why there was a difference in the energy of the two levels, you would be easy to answer. You would say that energy is indeed conserved. And the reason why the energy is increased is because we're actually doing work on it. And therefore the system is no longer isolated. And that makes sense, but not the mass one. Until you remember this equation. That total energy and mass are conserved, as opposed to saying that the total energy and the total mass is conserved. So you get the idea that because you did work on it to lift the bucket up, and some of that work became potential energy, it is justified to say that some of that energy may have become mass. So, total energy and mass conserved makes sense, and the same thing can be applied to the dismantling of the nucleus, because there was a strong nuclear force holding the nucleus together. You had to do a lot of work to dismantle the nucleus, to split apart the individual nucleons that were attracting each other with a great deal of force. So now the potential energy of those nucleons had increased, and so had their mass, because some of that energy may have been converted into mass. Hopefully making sense. So if someone were to ask you to find out the value of the nuclear binding energy of a particular nucleus, you find out the mass defect first. That is the difference between the mass of the individual components and the mass of the whole nucleus, right? And you need the difference to be in kilograms. And then you use this equation. You put m over here and you multiply it by c square, and c is the speed of sound with a value of 3, speed of light with a value of 3 into 10 raised to the power 8. And to get nuclear binding energy per nucleon, you simply divide by the total number of nucleon in that particular nucleus, and that is what this equation is all about. And another example in which all that difference in mass thing comes up is when you have a particular nucleus, and said nucleus splits apart to form, say, two products. So we may have had a parent nucleus A, and we got two products from it, B and C. And C was the much lighter product, and A was in a high energy state, and that reason being why it was split apart in the first place. B was comparatively in a lower energy state and C was projected with a huge kinetic energy. And what might be confused when they realize that the mass of B and C is actually less than the mass of A. But the explanation is simple enough. Some of the mass has been converted into the energy, the kinetic energy of product C. And so while both energy and mass have been conserved, mass apparently by itself has not been conserved. You have to understand the significance of the term mass defect and mass excess in nuclear reactions. And mass excess is basically the difference, the exact opposite of defect. Defect is when you have a decrease, excess is when you have an increase. Same principle applied slightly differently. You have to be able to represent simple nuclear reactions by nuclear equations of the form. So these have to be conserved, that is the atomic mass, and the atomic number must similarly be conserved, and these are principles you need to apply, and everything else is fairly simple. Define and understand the terms mass defect and binding energy, and sketch the variation of binding energy per nucleon with nucleon number. Just give me a second. I'll conjure up some sort of a diagram. So here we are, we have this graph, we have nuclear energy at the bottom and binding energy on the y-axis. So from what you can observe is that in the beginning, as the nuclear energy increases, so does the nuclear binding energy. So the greater the nucleon number, the more stable the nucleus. But then afterwards there seems to be a slow but gradual fall. Hopefully this is fairly obvious. And the one thing you need to know is the link with fission and fusion. So fission is when a large nucleus breaks up into smaller fragments, and fusion is the opposite, when smaller fragments build up to form a larger fragment. And why do some substances undergo fission and some fusion? Well, it has to do with the binding energy. Substances want to be in a state or in a form where they have a high binding energy and a low potential energy. So something will only undergo fission to form fragments whose individual binding energies are higher than that of the parent nucleus. And in the case of fusion, the large daughter nucleus that is formed would have a binding energy than either of the individual fragments that made it up. Hopefully this is making some sense to you. Fission and fusion was already studied in veritable detail in, I believe, O levels, and there is this arrow shown in this book I use, and it's here and it's written fission. And what does this mean, fission? Fission is when things join up. So smaller fragments till a certain level, till about here when there's an increase, for example, they're undergoing fission because comparatively till a certain point the larger fragments are having a greater binding energy per nucleon, whereas the larger fragments are undergoing fusion. I actually wrote the opposite here, should be fusion. And the larger nuclei, they are undergoing fission. And why are they undergoing fission? Because they want to break up into smaller fragments, because here we have a trend that the substances with the smaller nucleon number have a higher binding energy. So here, and they're preferring fission. Fission, and over there they're preferring fusion because the end goal is to be in a state which has the higher binding energy. What is meant by nuclear fusion and fission? Hopefully you already got that much. So done, and also done again, hopefully. Sometimes physics really messes me up. And this is for the really tough part of it, which frankly I sometimes love and sometimes I hate with a passion. So we have to infer the random nature of radioactive decay from the fluctuations in count rate. So what the hell does that mean? Well, what it means is that while in O levels you had a general idea that of half-lives, and that in a particular half-life this many nuclei would have disintegrated for a particular sample type. But the thing is that the only reason we have something of an estimate for each half-life is because whenever we get a large enough sample of something, things sort of like they get a pattern, and you get set probability values. Confused? Let me repeat. Say if you have 10 coins and you like flip them to get either a head or a tail, there is literally nothing in the favor of a head over a tail or a tail over a head. The chances of any of them happening are 50 to 50. Right? But you'd already guessed you'd never get the 50-50 proportion. You might get 1 tail, 9 heads, 3 tails, 9 heads, 7 heads, whatever. And you may then have 100 tosses and you might get 70 to 30, or if you're lucky you may get 40 to 60, but there wouldn't be a trend. But if you were to scale that up to 1000, you might get 400 to 600 or 450 to 650, and the probability is getting closer and closer to 50%. Theoretically speaking, if you get a large enough sample, even though there is literally nothing favoring head over tail, and the chances of getting either is 50 to 50, you would start getting a 50 to 50 difference, 50% in a particular orientation and 50% in the other possible orientation. And the same is true for count rate. And because half-lives tend to have a large value, say 25 days, that is why each time you get the same number of nuclei disintegrating, or estimately the same number. Because while disintegration is a totally random process, you can never tell when a particular nucleus, or more accurately, you can never tell when a nucleus would disintegrate next. We just had a nucleus disintegrate, the other disintegration might happen a second later, 2 seconds later, 3 seconds later. Really, it depends on the nucleus. And the disintegration is a completely random process. There is no pattern to it. The individual nuclei are doing whatever they want. And the first part is randomness. And that is why, while you may expect to get this whole smooth curve thingy, exponential decay always seems to portray it like this. The reality is that the curve is more of, while there is this general, shape of the graph which is the same as this, but there are these fluctuations, these ups and downs, and this is due to the random nature. So you literally never get a 50-50 proportionality, though you may really get close to it. So this is why, what is random nature? Now we have to be able to show an appreciation of the spontaneous and random nature of nuclear decay. Hopefully I already explained in sufficient detail why it is random. Why is it spontaneous? Because the nuclei, they're doing whatever they want, independent of each other, independent of their neighbors, and independent of any external condition. You can never influence them to disintegrate. They will disintegrate in their own time, and the probability of any nuclei disintegrating is the same in a particular sample. You cannot make the probability of a particular nucleus disintegrating more or less. You just can't do that, because they're really independent creatures, I guess. So to summarize, nuclear decay is random because it is impossible to predict when a particular nucleus in a sample is going to decay, and because each nucleus has the same chance of decaying per unit time. So because there are, say, 500 million nuclei in a sample, and the chances of any one of them being the next one to decay are the same, the probability of any one of them decaying is the same, and therefore it is impossible, because neither nuclei nor any external factors are favoring a particular nucleus. So you can never tell when a particular nucleus is going to decay. It could be the first, it could be the last. And to summarize, nuclear decay being spontaneous because the decay of a particular nucleus is not affected by the presence of other nuclei, right? And the decay of the nuclei is also not affected by chemical reactions or external factors, say temperature or pressure. So these get a bit confusing, so I recommend that you remember these 4 statements I just said, because otherwise, no matter how great your concept may be at the moment, you'd end up messing things up. And while I do not promote memorizing stuff without understanding it, sometimes it is better to summarize certain things, because if you get your concepts a bit messed up, because you would have that memory, you can infer what is true and what is not. So we have to be able to define activity, something called the decay constant, and recall and solve problems using A, lambda, n. So activity is basically, what is it? It's basically how active a sample is, or more accurately, it's the rate at which a particular sample is disintegrating, right? And we measure it in units that are called 1 becquerel or 1 or per second. So basically they're the same, you cannot use either one of them. And A is lambda n, A being activity and lambda being something called the decay constant. And when we come on to something, what is on earth is n. N is the number of undecayed nuclei. These are the ones that are yet to decay. So the activity of a sample depends on how many nuclei there are that can decay, that may decay, right? And it also depends on something called decay constant, which is the probability of a nucleus decaying, or the probability of an individual nucleus decaying per unit interval. these are a bit difficult, and I suggest that you remember the definitions. Decay constant has the unit same as activity, because this is merely a number, has no unit, and if this is per second, this is similarly per second. And is the probability. So if we have 5 nuclei in a sample, what do we want? What is the probability that an individual nucleus will decay per unit time? So if the whole complication of per unit time wasn't there, and you just wanted to know what was the probability of this being the one to decay, it would be 1/5. Same as for this, same as for this, and same as for this. So don't complicate yourself with what the hell does that mean, because it's complication. For A-levels, I suggest you that just get a grip of the definition. They aren't going to ask you to really go into detail about the decay constant. And just remember the definition. It is a probability, this is a sample, that say this one, the probability of an individual nucleus decaying per unit time interval. So when this is the reason that activity decreases when the process goes on. So initially, when there are a lot of undecayed nuclei in a sample, the activity would be high, but as time went onwards, the activity would decrease just as the number of undecayed nuclei decreased, and the count rate would similarly fall. So count rate, activity, and undecayed nuclei actually have the same graph. So if this were time in seconds or hours or whatever more, this type of graph could be for the count rate represented by R, could be for N for the undecayed nuclei, or A activity, because when N decreases, so does A, and lambda is a constant for any particular sample. For a carbon-12-6, it would have a particular value. For some other radioactive sample, it would have some other value. So I'm reading this part of the paragraph from the book because while it's a bit difficult to grasp, keeping it in your mind, you eventually get it. So because of the spontaneous nature of radioactive decay, we have to make measurements on very large numbers of nuclei and then calculate averages, because if we want to find out the probability of a particular nucleus disintegrating, we won't be able to do that easily, because there is literally nothing that is favoring that particular nuclei over something else. That nucleus is no special snowflake. It is completely normal, completely the same. One quantity we can determine is the probability that an individual nucleus will decay in a particular time interval. For example, we observe 1 million nuclei. So we have this sample, this radioisotope, and there are a portion of it we're observing in which there are 1 million nuclei. So we observe that after an hour, 200,000 have decayed, right? So in an hour, 200,000 have decayed, and from that we get the idea that perhaps in the next hour the same would disintegrate again, because this is a large enough time interval, and we may now start observing patterns. So the probability that an individual nucleus will decay in 1 hour is then 0.2. And how do you get that? Because we have an hour and the number that have decayed are this much, and the total number that were and had the potential to decay, but not all of them that decayed were this much. 1 million has 6 zeros, something you maybe you know, but you will still forget about it, likely. I'm sorry, this is 200,000. So this cancels out, this cancels out, and 2 over 10 is 0.2. And what do you get from that? You get that the probability of a particular nucleus in the sample decaying in a time interval of 1 hour is 0.2. That is 0.2 per hour is the lambda, because we observed that in an hour when we had a sample size of 1 million, all of which were equally capable of decaying, 200,000 of them did so. And when we take a ratio, we get that 0.2 of them actually decayed. And because any of them could have decayed and this much decayed, so you get the idea that this is a probability that a particular nucleus would decay in a particular time interval. So as I mentioned before, both this and this have an impact on the activity. So if we have a larger value of this, which means that a larger number of nuclei disintegrated in the same time interval, so if we have a larger number of lambda, we would have to have a larger value of this. Then the activity would be greater because there would be more disintegrations per unit time. Or if we had a larger number of this, then there would also be greater activity, because while this would be constant, because this is constant for a given sample type, we are multiplying it by this. So the greater the value of n, the greater would be the product of lambda n, and hence the greater would be the activity. This part really gets me confused, even though I really try hard to remember all of this. Hey, it's part of being a human being. Don't save. Activity. Again, so activity is the rate of nuclear disintegration, and decay constant is the probability that a particular nucleus will decompose in a particular time interval. And how do we get the value of lambda? Because the probability of any nucleus in a huge sample decaying is the same, because this is a spontaneous process. If we take a long enough time interval, say 24 hours, and observe the amount that decayed in that 24 hours and divided it by the total sample size, we get an estimate of the probability of a particular nucleus decaying in that time interval. We have to infer and sketch the exponential nature of radioactive decay and solve problems using x naught e to the power minus lambda t, where x could represent activity, number of undecayed nuclei, or received count rate. So x could be activity, could be undecayed nuclei, could be count rate. So actually this is sort of equation describes a graph of this type. And because I said on the y we could have a, r, or n, it makes sense that this kind of formula can be used for any of the two types. This is fairly easy. We just have And x naught is actually the initial activity or the initial count rate. That is when time was 0, when the reaction had not actually begun, the decay process had not started. And t is the time interval after the decay process has begun, and we want to know what the activity or the count rate or the number of undecayed nuclei are at that point in time of the reaction. And defined half-life is basically the amount of time it takes for the number of undecayed nuclei of a sample to halve, or the activity to halve, or the count rate to halve, and it is a constant mainly because we are taking a long enough time interval, and even unbiased probabilities get a pattern if the sample size or the sample time interval is long enough. And you have to solve problems using the relation lambda is 0.693 over 2. So you get the idea that for any reaction, the product of the decay constant of said reaction and the time interval of that same reaction is the same. And that is why these are extrinsically related, because if this increases, then the other one would likely fall. And why is that? Lambda increasing, what does this suggest? It suggests that for a given time interval, the probability of a particular nucleus disintegrating increases. And that means that it is more likely that more nuclei would likely disintegrate in the same time interval. And because of that, the half-life would obviously fall, because there would be less time needed for the sample size to halve at any time interval. Hopefully, again, you're getting what I'm trying to say here. And then there's the whole, how do you actually get this? I mean, how do you get this formula? So we have this, n is equal to n naught e minus lambda t. N is the undecayed nuclei. This is the initial number of undecayed nuclei. And something I forgot is this, that A can also be delta n over delta t, that is the change in the number of nuclei over delta t, which is actually only useful when we assume that delta t is a small in time interval, say a few seconds. So what do? You have n divided by n naught, and you're assuming that t is actually the first half-life, or whatever half-life actually, and therefore n would actually be 1 by 2 n naught. And what you do is you basically divide this by n naught and divide this by n naught, and when you do that, you're just left with 1 by 2 e minus lambda t. And what you do, you want this e to disappear, and so you take the natural log, and when you do that, when you take the natural log of 1 by 2, it becomes natural log 1 minus natural log 2, and because natural log 1 is actually equivalent to 0, you're just left with minus natural log 2. And because e has disappeared, on this side you have minus lambda t, and because, as I mentioned previously, we're doing this for half-life, this is lambda t half-life. The minus minus cancels, and because if you take the log of 2, you get 0.693, so you can say 0.693 is equivalent to the product of the decay constant, which is the probability of a particular nucleus decaying in a unit time interval, multiplied by the half-life, which is the time taken for the sample size of a radioactive sample to do half. And hopefully this was helpful. Let's just go over a few questions to see how much we got. So the sun releases vast amounts of energy, you know that. And we say that its power output is 4 into 10 raised to power 26 watt. So we have to estimate by how much its mass decreases each second because of the energy loss. And before you get confused at this moment, just assume that energy has mass. So go by that idea. So power is what? Power is energy over time. And energy is power into T, and because we're taking it for 1 second, we can just have P into 1. And so energy can be taken as 4 into 10 raised to power 26 joules energy is lost per second, right? And you know this whole E is equal to mc squared shenanigans, right? And you want to know the loss in mass per second. So what you do is you basically divide this value of E by c squared, and the value you get is the mass, and it will be in kilograms. And you'll probably get a very small value, so don't get freaked out. And we also have to calculate the energy released if a helium nucleus is formed from separate protons and neutrons, right? So as I mentioned previously, that the dismantled form appears to have greater mass compared to the actual nuclei. So how many nucleons do we have? In helium we have 4 of them, and you have to know that the actual values of the mass of proton and neutron are actually slightly different, and you have to use those because we're doing very precise workings in this stage of A levels. So you 2 multiply by the mass of the proton given in the data booklet plus 2 multiply by the mass of the neutron given. And what do? You minus this from the mass of the helium that would be given in the question, and you would get the answer you want. So if a golf ball has a mass of 150 gram, to calculate that into kg, calculate its increase in mass when it is traveling at 50 meters per second. So we have the speed, we just put 1 by 2 mv squared to get the energy, we equate it to mc squared, we divide E by m, if you divide E by c squared, we get the mass. So they're asking what is this a percentage of its rest mass. You simply divide the answer you got from 150 and multiply by 100, given that the answer you've gotten is in grams as well. And these are pretty easy questions, but I suggest you do them because we forget so much easy stuff. So when we studied the whole Nucleon number graph, you'd be surprised that the H11 does not appear on the graph, and you'd be stumped and you'd be like, why not? Use that brain of yours, why not? Well, it's because the H11 isotope doesn't actually have a neutron, and it is nucleon number against nucleon energy, binding energy. And obviously where on earth would we put that? It would be difficult to put it at what, 0? That would be hell of confusing. So we know the mass of a beryllium 8 nucleus, and we know that the proton mass and the neutron mass. And we need to determine the mass defect, which would again be the difference, the binding energy, which would be E is equal to mc squared. And the binding energy per nucleon would simply divide the value we gotten from the total number of nucleon, which happens to be 8 for the beryllium nucleus. And so there's a question, we have to use the binding energy graph to suggest why fission is unlikely to occur with light nuclei, because fission is when things break apart, right? So lighter nuclei, for that lighter nuclei, as the nucleon number increases, so does its stability, so does the binding energy. So if a lighter nuclei is to split apart into smaller fragments, the smaller fragments individually would have lesser binding energy than the parent nucleus, and this would not be good, because what we want is to have products which have the higher binding energy, and this is why this is unlikely to happen. So if we have a sample of carbon-15, which is a radioisotope, it has like 500,000 undecayed nuclei, and we know that the decay constant is 0.3 second. How do we determine the initial activity? What would we do? We'd simply multiply the decay constant with the initial undecayed nuclei. Simple, easy use of the formula that was given in the syllabus. So we have a sample of radius, and it has a count rate of 20 counts per minute. And it is known that the counter detects only 10% of the decays, because we can't have it all over the place, and decays is happening throughout every angle of the sample. And the sample contains 1.5 into 9 undecayed nuclei. What we need is the decay constant. We want to determine it. So this is a bit of a complicated question, and if you attempt doing it in your mind, you'd likely make a mistake which you normally wouldn't have if you had gathered your knowledge or written it down, which I prefer doing, because in exam you're often not at your best. You're confused and you're pressure, and you miss things out unless you have written them down. 20 counts per minute. And if this is 10% of the actual number of counts, we can say the 20. So if 10% is 20, then 1% is 2, and 100 is 200. So we actually have 200 counts per minute happening. Alright, and the sample contains this many undecayed nuclei. Oh, 1.5 into 10 to the power 9. And what do you want us to know? We want to determine the decay constant. Like I said, A is delta N and we want this in whatever form. So if we put this over here and we put this over here, so lambda would be simply be R over N. They're basically the same stuff. Getting confused over them is not a good idea. So for exponential decay, as you previously known, we can have N is equal to N naught E minus lambda T, and N naught is the initial undecayed nuclei, and N would be the remaining undecayed nuclei after time interval T, and lambda is the decay constant as before. And you really need to be careful with the signs. If lambda is in per second, then time needs to be in seconds. So if we use this, the value of the lambda would be similarly be per minute. And as I said, the activity of a sample is proportional to the number of undecayed nuclei. And is also proportional to R. So if a radioactive sample is known to emit alpha, beta and gamma radiation, we have to suggest 4 reasons why the count rate measured by a Geiger counter next to the sample would be lower than the activity of the sample. 4 reasons: there would be absorption, because alpha radiation tends to not be very penetrating, and if there is substantial distance, a lot of it would have been absorbed by the air molecules, because it hasn't been specified how much distance we have. And there is also the possibility that there may be something in between. For example, there may be a glass sheet which could be blocking some of the radiation. Then there's also the fact that the radiation is happening in all directions, and we only have Geiger counter placed at a particular orientation to the sample. And then there is the fact that a Geiger counter can only be so sensitive, and there's a lot of decays happening, and depending on the sensitivity, only some of it may actually have registered. So if there is beta decay going on and we have an activity of 2.8 into 10 raised to the power 7 becquerel, again remember the SI units, we have to estimate the number of beta particles emitted in a time interval of 2 minutes, and you'd be confused, but then you remember that we have another formula for A, which is delta N over delta T, and we simply multiply A with delta T to get delta N. Another question: if we have a sample which has 1000 undecayed nuclei and decay constant is 0.2 per second, we want to know the initial activity. A would be delta N minus delta N, because there's a decrease in it. We simply multiply the decay constant 0.2 with the undecayed. Now they're asking us to determine the activity after 1 second, and you might make a mistake and say it is the same, but remember, activity follows an exponential decay pattern, because as the number of undecayed nuclei fall, so does the activity, so does the count rate, so does whatever. So how do you figure this out? So we have, better get a new one. We have the initial activity, which is 200 becquerel, and afterwards we won't have that much. And we know that how much afterwards, we want to know what that is. And we know that we have a number of equations. We have A is equal to A naught E minus lambda T, because we have calculated the initial activity and we know the value of the decay constant as being constant, and we know the time interval. We can simply put this and we'd get the answer. And let me just find a calculator. Yep, you get the answer you want, and this is a simple way of application of whatever knowledge that you have garnered till this point. But there is another way. So, because after 1 second we might expect 800 nuclei to remain undecayed. Why is that? Because if we have 100 undecayed nuclei and 0.2 per second, and like I said, another way of getting the lambda is to have, if we want the lambda in per second, we get it by having the total number of undecayed nuclei and the number that decayed in that second, and we multiply by it 1 by 100. And because we have 0.2 and we initially have 1000, so to get a value of 0.2, 200 would need to have decayed, and so in time interval of 1 second after a time interval of 1 second, we would have been left with 800 nuclei. And this is it. Hopefully this was helpful. If it wasn't, please feel free to criticize, as long as it is constructive criticism. If you like, please like, subscribe, and please comment. Thank you.